We're going to take a look at the fundamental theorem of line integrals, and I want to examine this question first. So let's go ahead and solve it using the standard strategy. So before we determine if it is a conservative vector field, let's just go ahead and use brute force. So I'll need to figure out what dx and dy are, so let's discuss that. Well, we know we're going to substitute t for x and t squared plus 1 for y. So then I can certainly get dx dt and dy dt. Dx dt is 1. Dy dt is 2t. So what is dx? Dx would be dx dt dt. Similarly, dy would be dy dt dt. So dx is 1 dt and dy is 2t dt. So we're going to go ahead and make that change. We're going to substitute in t whenever we see an x, t squared plus 1 wherever we see a y. Dx will be 1 dt, dy will be 2t dt, and t will range from 0 to 2. So let's rewrite that integral. So 5x becomes 5t minus y becomes minus t squared plus 1 plus 3. Dx is 1 dt. T ranges from 0 to 2 minus another integral as t goes from 0 to 2. X is t minus 4y. Y is t squared plus 1 plus 5. Dy is 2t dt. These integrals are not terribly difficult, but let's go ahead and use technology for expedience sake. So the first integral, 5t minus t squared plus 1 plus 3 times 1 dt as t goes from 0 to 2. And Wolfram alpha gives us 34 thirds, so let's write that down. So we have 34 thirds minus, what will the second one be? Integrating t minus 4 times t squared plus 1 plus 5 times 2t dt. As t ranges from 0 to 2, we get negative 68 over 3. So adding those together, that gives me 102 over 3, which equals 34. Now, the goal is to also solve this with the fundamental theorem of line integrals if it is possible. Remember, it's possible if we can find a potential function, which means if the original vector field is conservative, we can solve this with that theorem. I want to rewrite this original problem as a f.dr problem, so it is indeed going to be work. Work will be the integral over c. What is my vector field? 5x minus y plus 3 in the first column. Be careful with the negative sign here. So that's negative x plus 4y minus 5 dot dx dy, fine. And we recognize, of course, that work is the integral over c of f dot dr. Now, when can I use the fundamental theorem of line integrals if that vector field is conservative? So let's consider that. If this is a conservative vector field, there will be a potential function, little f, whose gradient will equal that vector field f. Now, the gradient of little f is f sub x, comma f sub y. And the way that we proved something was conservative previously was to show that its curl is 0. And you certainly could do this, even though we only have 2 dimensions. But it's much simpler to keep something in mind, namely that the mixed partials must be the same. F sub xy and f sub yx have to be the same for these nice functions. So if this equals f sub x, so assume, for the sake of discussion, assume that we have f sub x is 5x minus y plus 3. What would f sub xy be? What's the partial with respect to y of this? That's negative 1, okay? And similarly, assume f sub y is the second piece. Assume f sub y is negative x plus 4y minus 5. What's f sub yx? What's the partial with respect to x of this? That's also negative 1. These agree, therefore this function will exist, therefore the vector field is conservative. So that's helpful. That enables me to use the fundamental theorem of line integrals. Let's just sort of give a general statement here. If I have a vector field F made up of M in the first slot and N in the second slot, and if M sub Y equals N sub X, if that happens, then F is conservative, which enables us to find the potential function and enables us to invoke the fundamental theorem of line integrals. So let's try to find the potential function here for this vector field. There is my vector field. I want this first piece to be F sub X. I want the second piece to be F sub Y. So if that's the case, we're going to say that F sub X has to equal 5x minus y plus 3. So then what would F be, integrating this with respect to x? F of xy would be 5 times x squared over 2. So 5 halves x squared, y is perceived as a constant, minus xy plus 3x plus not a constant, but any function of y, plus g of y. Now let's go ahead and take the partial derivative with respect to y of that. So again, partial derivative with respect to y of 5 halves x squared minus partial derivative with respect to y of xy plus partial derivative with respect to y of 3x plus partial derivative with respect to y of g of y. So f sub y is 0 minus, with respect to y, that's x, plus with respect to y, that's 0, plus the partial derivative with respect to y of g of y is just g prime of y. So this is telling me then that f sub y is negative x plus g prime of y. But looking up top, f sub y is supposed to be negative x plus 4y minus 5. If that's the case, that tells me what g prime of y is. G prime of y then has to be 4y minus 5. Which would tell me then that g of y is the integral of that. So 4y squared over 2, 2y squared minus 5y plus c. But I don't care about this c because I'm looking for a potential function, not all of them. So we're going to go ahead and we're going to add this g of y up to this position to get our potential function f of xy. So there is what we believe our potential function is, but let's go ahead and determine its gradient and see whether or not it matches capital F. Little f sub x, 5 halves times 2x, which would be 5x, with respect to x, with respect to x, with respect to x, 0, 0. So we get 5x minus y plus 3. That matches in the first slot. How about the partial with respect to y? With respect to y, that's 0. With respect to y, that's x. With respect to y, that's 0. With respect to y, that's 4y. With respect to y, that's negative 5, which of course is negative x plus 4y minus 5. So our gradient of f is indeed, as expected, 5x minus y plus 3 and negative x plus 4y minus 5. So f is the potential function of capital F. So what does the fundamental theorem of line integrals tell me? If I evaluate the potential function at the end point and the starting point and subtract, that will give me the work. So there's the original question, and there is the potential function. So my starting point will be r of 0. Plugging in 0, t is 0, t squared plus 1 is 1. That's my starting point. If I plug in the ending point, r of 2, t is 2, t squared is 4 plus 1 is 5. So I need to determine what is f of 0, 1 and what is f of 2, 5. Let's do the 2, 5 first, because we know that the work, according to the fundamental theorem of line integrals, will be the potential function of the endpoint minus the potential function at the starting point. So we need to find out what is little f of 2, 5. What do we get? Going to technology, what do we see? Evaluate 5/2 x squared minus xy plus 3x plus 2y squared minus 5y when x equals 2, y equals 5. We get 31. That's my endpoint. Now my starting point is 0, 1. What is f of 0, 1? Let's again go back to technology. And you'll notice we get -3. So f of the endpoint minus f of the start point, the work will be 31 minus -3, which equals 34. So we know our informal notion of the fundamental theorem of line integral. If we have a conservative vector field, we evaluate the work by determining the potential function, evaluating at the endpoints, and subtract. Let's formalize that a little bit here. So formally, suppose that big F, which is m in the first slot, n in the second slot, is a conservative vector field in some region containing x0, y0, and x1, y1. So let's pause in our formality for a minute. We know it's conservative if the curl of f is 0, or we said the mixed partials are the same, namely m sub y equals n sub x. If we have a conservative vector field, this will hold. And again, it's conservative where? In some region containing those points. Now, what are those points? This will be the starting point, and this will be the end point. So continuing with our formality, in some region containing x0, y0, and x0, y0, and m and n are continuous functions on this region. So what do you have to keep in mind there? Well, you can't have a division by 0 thing happening, right? If you're going to draw a circle around x0, y0, and x1, y1, you can't have a situation where you have a division by 0 thing happening there. So be careful there. And what else are we going to say? And the gradient of little f equals big F, which of course, what does that mean? That means little f is the potential function. And what do we say about C? And if C is any piecewise smooth parametric curve that starts at x0, y0, and ends at x1, y1, then what are we going to say? What is our conclusion? Then work, which is the integral over that curve C of f dot dr, is evaluate the potential function little f at the endpoints and subtract. The ending point is x1, y1. The starting point is x0, y0. So that is a formal statement of the fundamental theorem of line integrals. Short form is if you have a conservative vector field, find the potential function, evaluate at the endpoints, and subtract.